Thanks.
Okay. Okay. Welcome to this is a lecture in Beyond the Standard Model physics. Okay, selected topics in Beyond the Standard Model, number 4. Okay, and I stopped at the point when we introduced black holes and recalled some of the main some of the important features that black holes have. So let me reiterate why black holes are important for the, in particular, of course, they are important because they exist and they are part of nature, and they are fascinating objects gravitationally. But from the point of view beyond the standard model physics, and in particular topics, some puzzles within the standard model, so they are important because of the following reason. So in semi-classical limits that we discussed yesterday, so in semi-classical limits, right, which we defined as a limit when mass goes to infinity and Newton's constant goes to 0, but R is fixed, okay, is fixed finite, so meaning that this is a limit of fixed, or if you want, rigid geometry. So this is a limit of 0 back reaction. So h bar is still 1. We keep h bar 1, or whatever finite quantity you want. And this is the limit of 0 back reaction, we said, right? So this is also a limit of 0 back reaction from a quantum particle to the geometry. And so in this limit, in semi-classical limit, there are certain properties of a black hole that are understood exactly, okay? So in this limit, certain features, certain properties are understood exactly, basically, okay? For example, thermality of Hawking radiation. Also, properties that are called no hair, okay? So the absence of measurable quantum numbers that could give us information about the interior of a black hole, other than gauge quantum numbers, charge, mass, angular momentum, and maybe some other quantum Aronoff bomb type quantum hair, okay? So now here's the situation that we have this limit, okay? Now in this limit, the entropy of a black hole, Bekenstein-Hawking entropy, which is an intrinsically quantum notion, because entropy counts the degeneracy of microstates of a black hole. It's a logarithm from the number of degenerate microstates. So the entropy, which is mass divided by Planck scale squared, of course, in this limit, since G Newton goes to 0, also Planck scale goes to infinity. Okay, so the entropy goes to infinity, right? And so certain properties are known exactly, right? And because of this, then once we go away from this limit, so therefore, for finite values of the parameters, finite but large entropy, okay? The back reaction at least for some initial time, must be small. Okay. Now, small, what does it mean, small? So entropy is entropy is a measure of quantumness. So it is a measure of strength of back reaction. We can also express it in other parameters, but entropy is a convenient parameter. So when entropy is infinite, back reaction is 0. Okay. When entropy is finite but large, back reaction obviously is expected to be small, at least for limited time. Okay. For short time intervals, back reaction is expected to be small, and correspondingly, the corrections to the properties that in semiclassical limit are exact, are expected also to be small. Okay. Now, of course, are expected to be small as long as we are in the regime of weak field, weakly interacting Einstein gravity. And this is very important. So let me repeat this story. So there is a property of a black hole. So we have a black hole. And so there are certain properties that this black hole we know exactly in semiclassical limit. And now we go away from the semiclassical limit. So the semiclassical limit we can characterize as the limit when R is the size is fixed. Okay, R is finite. And semiclassical limit is when entropy is infinite. Now, correspondingly, these properties, we expect that the corrections to these properties, are of order, if they are expected to be analytic in 1 over S expansion, and corrections are to be of order of 1 over S, okay? Or higher order, but small, okay, compared to the semiclassical limit. So correspondingly, those properties that we can derive in semiclassical limit exactly for real black holes, which have finite mass, and correspondingly they have finite entropy, those properties must be approximately very good, okay? At least for some finite time intervals, okay? Now, therefore, assuming that assumption, so making this assumption that corrections must be small. Now, corrections must be small as long as we are in weakly coupled Einsteinian regime of gravity, okay? As long as weakly coupled gravity means as long as alpha gravity for the given scale of the black hole, this means that alpha gravity evaluated for the momentum transfer of 1 over R is weak. Okay, so if alpha gravity evaluated 1 over R is weak, we expect that the correction should be small. Correspondingly, now, if this assumption will lead us to a contradiction, now we can build up some thought experiments. And if this assumption will lead us to a contradiction, this is an indication that we are no longer in weakly interacting Einstein gravity, okay? And so, therefore, from this point of view, black holes are extremely powerful tool for setting the validity domain for weakly interacting Einstein gravity. Of course, when weakly interacting Einstein gravity couples to the standard model, okay? So, therefore, here is the validity domain. So here we have DSM, some beyond the standard, some extension of the standard model, of course, plus Einstein gravity, okay? And so this theory VSM plus Einstein gravity has certain domain of validity. Okay, so this is domain of validity. And black holes are indication, very useful tool for understanding when we are crossing this domain of validity. Okay, so black holes can give us an indication about the boundary of this domain. Okay, I will give you an example now of this, which is very useful, in particular for addressing a certain puzzle of the standard model, a hierarchy puzzle. So the example. So this is example is bound on the number of particle species. Let me denote this bound by NSP. Okay. So let me define NSP. What is NSP? So we are with, let's say we are at certain scale. So we are, let's say, within this domain of validity. So let me assume that we are within the domain of validity of Einstein gravity, weakly interacting Einstein gravity. Okay, and at some scale L, all right. And so at that scale, there are certain number of active particle species. In other words, there are number of particle species that are lighter, that have mass comparable or lighter than the scale 1/L. Okay. So why is this number important? Because these species will participate actively in the processes, in particular in gravitational processes, interactions with momentum transfer. So they are active in the processes with momentum transfer, Q, with momentum transfer, Q, sorry, larger or comparable to 1/L. Okay. So this will be the active species. So let's say at some scale L, and of course, the scale L obviously must be below, I mean, the larger than the length scale beyond which the weakly interacting Einstein gravity goes out of the regime. Okay, so we want to understand where is that boundary. Okay. So now it turns out that black hole physics puts a very severe bound on the number of species, or equivalently relates the number of active species to the boundary of that domain, okay, to the length scale beyond which weakly interacting Einstein gravity description in terms of weakly interacting Einstein gravity breaks down. Okay, so so there are many arguments. Of course, I don't have time to go through all of them, but there is one argument, for example, very clean from black holes. Okay, so let's take a black hole of certain radius r. Okay, right? And so this black hole, we understand that semi-classically it evaporates in the thermal spectrum, but even non-semi-classically, as long as the radius of a black hole is much larger than the Planck length. Okay, Planck length. In pure Einstein, the evaporation will be approximately thermal. Okay, so the corrections will be small because if the size is much larger than the Planck length, the entropy of a black hole is much larger than 1, because entropy scale says black hole Bekenstein-Hawking entropy. This scale says, as we said, the surface area in units of the Planck length, for example. Okay. So the approximation should be, so the evaporation should be at least approximately, should be thermal in a very good approximation. Okay, at least for initial times. Now, when time goes on and the black hole loses half of its mass, at least half of its mass, the evaporation, we cannot assume that it remains thermal. We cannot make that assumption because there are all the indications that that cannot be the case. But we are not entering there. It's sufficient to think of evaporation at some initial stages, a young black hole of the size R. Okay, so very conservative assumption. Okay, framework. Now, so here what happens is that there is a temperature, right? Temperature is given by the, I'm ignoring the factors of 4 pi and so on. So temperature is given by the inverse Schwarzschild radius, okay? Or, which is the same thing, is given by the Planck scale square divided by the mass of a black hole, okay? All right, so now we have Stefan Boltzmann law of this evaporation. So mass changes, mass decreases, and decreases as minus t square times the number of species. And here comes the important thing about thermality. Since the evaporation is approximately thermal, evaporation is democratic in species, to the leading order at least, okay? So democratic in species. And so, of course, we assume that these species are active at the scale of temperature T, right? And so the temperature, so from here, so from here, it's clear that mass is inverse of temperature, and correspondingly, derivative of the mass, dot is time derivative. The derivative of the mass has an interesting expression. We can express it in an interesting way, that this is 1 over, this is T dot over T square. Now, T dot over T square is a very important quantity, okay, as I will explain in a moment. All right, so now we can express this expression as, so we can take this, plug it here, and we'll get that T dot over T square is given by number of species times T square divided by the Planck mass square, okay? So we got this expression. Now, why is this expression important, okay? This expression is important because of the following reason. Notice that the parameter, this parameter, T dot over T square, this is a parameter of thermality, which for a black hole is the same thing as parameter of semi-classicality. Now, why? Because if I have a thermal system with some temperature T, okay? Now, the temperature is a thermodynamic quantity, and and temperature is defined in thermal equilibrium, okay? So temperature is a notion that strictly I can define thermal equilibrium. When temperature changes, okay, right? What happens is that, of course, if temperature changes adiabatically, so the system has time to readjust, okay, to the to equilibrate, then we can talk. We can speak about the temperature that changes in time. But strictly speaking, temperature that changes in time invalidates slightly the notion of temperature. Because since temperature is something in the strict equilibrium, and if temperature changes, this means that necessarily there is a departure from thermal equilibrium. The departure can be minuscule. That's why in ordinary systems, for example, in this room, of course, there is we're talking about temperature, but again, there is constantly exchange of temperature between room and the walls and exterior, and then temperature constantly changes. So of course, there is no real system that is in thermal equilibrium, but the measure of how good is the notion of temperature, how good is the notion of thermality, is given by this parameter. Okay. So in other words, if as long as change of the temperature is less than the temperature square, the system is approximately in the temperature is approximately a good definition, a good notion. Okay. Right. So, but this also tells you that when this parameter is much less than 1, we can talk about temperature reliably. So we can speak about temperature reliably. But this breaks down for the notion of thermality. Breaks down for T dot over T square becoming order 1. Okay. So when T dot over T square becomes order 1, this means that our system, our assumption that system is thermal simply is not a valid assumption. We have to go back and reconsider, change the system, introduce new degrees of freedom, do something. Okay, we have to do something in this area. Okay. Right. So now the question is, we want to understand when this happens for a black hole, and we have expression for this. We just derived it, right? So we have this expression, and we see that thermality parameter for a black hole is effectively given by the number of species and by temperature divided by Planck scale squared. Okay. So correspondingly, when therefore when so so correspondingly a weak field, weak coupling, Einstein gravity description breaks down when T dot, let me copy it again, which was number of species times T squared divided by M Planck square becomes 1, okay, becomes order 1. So for the critical temperature, so the critical temperature for which this happens, let me denote it by T star, okay? So this is T star, this is derivative evaluated to T star. So correspondingly, we have a cutoff temperature. So the cutoff temperature is, we can define it from this expression as Planck scale divided by number from the particle species, from the active particle species. In other words, okay, so let's try to understand what is happening. What is happening is this: if I have a black hole, so, and let me define this scale. Let me call this scale M star. So M star is a cutoff of weak Einstein gravity, weakly coupled Einstein gravity. Quantum Einstein gravity, weakly interacting, can no longer be applied to this domain. Okay, beyond the scale. So in other words, if I have a black hole of radius, which is R star, okay, if I have a black hole of radius R star or smaller, so naively, if I have large number of particle species, I may think that, but I can introduce formally, I can introduce arbitrary number of particle species, so that this scale M star could be arbitrarily low. Correspondingly, the corresponding scale, let's call it L star inverse, okay, could be arbitrarily long. So we can introduce a black hole of radius R, which is, let's say, inverse M star, okay? And naively, I may think that Einstein gravity should be valid, obviously, because this object is much larger than the Planck length, okay? This size is much larger than Planck length. But however, that's not the case, because of too many particle species in the theory, the collective effect So collective effect is too strong. And so collective effect tells me that Einstein gravity cannot afford to have this many particle species and still remain a weakly interacting quantum theory. Okay, so there is a conflict between the two, and so this sets the validity scale of semi-classical or quantum weakly interacting Einstein gravity description. Okay, so in other words, this scale m star is a cutoff of the theory. So therefore, the cutoff is that if I have a theory of beyond the standard model with n particle species plus Einstein, the cutoff validity domain is marked by the scale m star. Okay. So no process with momentum transfer exceeding or comparable to the scale m star can be described within the validity of weakly interacting, weakly coupled Einstein gravity, quantum Einstein gravity also, right? Okay. So let me take questions if there are any questions about this, because this is a very important point.
I have a question.
Yes, please.
Could you please elaborate a bit more on the idea that the collective effect is too strong? What do you mean by that?
Collective effect is, yeah, very good. So the collective effect is precisely this, the effect. Where is it? This one. So, right? In other words, what happens is that the way you can think of it is like this, right? So gravity is a universal interaction, okay? Okay, so collective, let's explain the notion of collective effect. Einstein gravity is a universal force, right? So remember we said that if I have graviton, canonically normalized graviton, interacts with all the energy momentum tensor, okay, of all particles with the strength suppressed by 1 over m Planck, okay. So correspondingly, we have defined, for instance, imagine, let's say I have some particle species which is non-gravitational, could be a boson or a fermion. So let's say some species, let's say psi, let's call it psi, a species, okay. And so the coupling strength here is given by 1 over m Planck, okay, of gravity. Or in particular, for example, if I want to consider Einstein, two gravitons, let's say annihilating two species, or coupling like this, okay. So these are controlled by alpha gravity, which is momentum transfer square divided by m Planck square. Okay, so both of these are controlled by this interaction, okay, by this coupling strength. However, so let's say this is number of species. But now imagine that here we're discussing situation when we have index of species, okay? So it's just not just one, but there is a J index flowing in this diagram, which goes from 1 to n sp species, okay? So this creates a concept of what I call collective coupling, and which plays important role whenever you have large number of species in the theory. For example, right? What is happening is that the graviton now, so two gravitons, right? Now, if I'm looking at the certain process of momentum transfer, two gravitons annihilating into two particles. Okay, let's consider this process, right? 2 in 2. The point is that this process, the number of final channels of annihilation is increased by the number of species. Okay, so correspondingly, for example, if I have two gravitons scattering into two particles, the rate of the process, okay, rate of two gravitons into two is enhanced by number of species, okay, is multiplied by number of species. So this is what is also happening in a black hole. In other words, what black hole does is that instead of thermally producing two particles, okay, the pair, let's say, instead of thermally producing pair of species of given flavor, now the number of channels in which black hole can evaporate is increasing. That's the collective effect. So effectively, there's a collective coupling. Sometimes we call it, if we take terminology for QCD with large number of colors, such a coupling we call Toft coupling. So I would call this a gravitational Toft coupling or species coupling. So species coupling. So we can denote it by lambda or Toft coupling, gravitational Toft coupling. Of course, I mean, there are some subtleties, differences. So we can define it as alpha gravity times number of species, number of particle species, okay? So in other words, what happens is the following thing, that there is a set of class of processes in which the strength of the process is controlled not by alpha gravity, but by collective, by species coupling, okay? So where alpha is enhanced by number of particle species. I can give you some examples. So without black holes, also this is also happening without black holes, okay? Black holes are simply a very powerful manifestation of this fact, because black holes, we know that they are non-perturbative objects, and the statements about that are non-perturbative, okay? But for example, the type of diagrams, bubbles, for instance, imagine graviton going into a particle loop and again into graviton, right? For example, this type of diagrams, this type of bubbles. So you can see what is happening, that each bubble, so each bubble brings a factor of alpha because there are two gravitational vertices. So right, each has 1 over m Planck, so it gives you 1 over m Planck square. So each bubble gives factor alpha, but then there is number of particle species floating in the loop. So there is an enhancement by number of species. So therefore, each bubble contributes. So if I have, let's say, L bubbles of this type, so the expansion is not expansion in alpha gravity, but expansion is expansion in lambda, or expansion lambda L, or which is the same thing as alpha gravity and species in power L. So for example, already this tells you that when lambda gravity becomes order 1, for certain scale where lambda gravity becomes order 1, of course, lambda gravity is scale dependent. Why? Because also alpha gravity is scale dependent. So when lambda gravity becomes order 1, the series have to be resummed. Something is happening with the theory. We cannot just continue unpunished in a domain with a strong lambda. Okay. There's a very interesting another set of diagrams which you can see. For example, there is a set of diagrams in which, for instance, two gravitons, all right, two gravitons producing, sorry. Two gravitons producing species in final state, okay? So when two gravitons go into the number of particles, final state particles, with the occupation number of final state particles being of the order number of particle species in the theory. So it turns out that something extremely interesting happens at this point. Well, what happens at this point is that this type of process saturates unitarity, okay? The way you can understand this is because since there are multiplicity of particle species labels, effectively this final state has a high entropy, high degeneracy. And correspondingly, two gravitons have many, many choices of producing final states with the same energy. So the species label, because we can have here species J1, here we can have J2, and so on, J and Jn, right? Okay, Jn over 2, okay? And so what happens is that the final state has a very high enhanced probability. Remember, in the previous lectures, we were discussing suppression when two particles go into n, right? Because there is a factorial growth. This is not an artifact of factorial growth. This happens at the point of optimal truncation. This is because there are simply too many final states in the final multi-particle state. And that multi-particle state saturates unitarity. Actually, I call this type of object a saturon. Okay, so this is another set of processes that is happening. So black holes, they are powerful too because they capture all this. So I don't have to go diagram by diagram because black hole is a non-perturbative object, and black hole tells me, I know unambiguously that if Einstein gravity is valid, black hole properties have to be corrected very little. Okay, thermality, etc. If that statement leads me to a contradiction, I know that I'm beyond the weakly interacting Einstein gravity. Okay. Does this answer your question?
Yes, thank you very much.
Okay, I have another hand. I see another hand, Emanuele.
Yeah, I'm a little bit confused about the relationship between thermality and semiclassicality. If you could elaborate a little bit more on this.
Yes. So here the connection is pretty simply straightforward, because what I told you, of course, in this course of lecture, I didn't derive Hawking computation. That computation is exact. Okay, Hawking did computation in the limit, in strict semiclassical limit, and that computation gives an exact result. Okay, so Hawking computation puts an equality sign. Hawking computation is done in exact semiclassical limit, and it puts an equality sign between semiclassicality and thermality of radiation. Okay, so that's the fact of that's a state of art, right? So correspondingly, it is the Hawking computation that sets equality between thermality of black hole evaporation and validity of semiclassical gravity, corrected little. It's not exact, obviously. We don't live in exact semiclassical world. We live in quantum world. Black holes have finite mass and finite entropy. But because in the limit of infinite entropy, Hawking computation is exact and it gives exact equality, we know that thermality must be a good approximation for within the domain where semiclassicality is a good approximation. Semiclassicality is a good approximation when theory is weakly interacting. Quantum theory is weak. If quantum theory is weak and you are considering a non-perturbative object in weak quantum theory, semiclassicality is a good approximation for those objects. Okay, so this is the connection. Okay. So connection equality is set by the Hawking computation, not by additional arguments. That's what sets equality between thermality and semiclassicality. Now, if you discover that your assumption of validity of semiclassicality leads you to somewhere else and shows that the black hole is not thermal, this means that semiclassical approximation was not valid to start with. And so, which means that we are beyond the cutoff of the theory. Okay, now this black hole argument, of course, is confirmed by huge number of quantum field theory arguments, direct computations, as I said, from the loops or scattering amplitudes. All right, this is all gives you the same picture. But as far as thermality, in the scattering amplitudes, you don't have to discuss thermality. Scattering amplitudes are just scattering amplitudes. You see that for certain number of particle species, certain set of amplitudes reliably computed again in weakly interacting theory, they saturate unitarity. Okay, so that's a different side of the same medal. Okay, does this answer your question?
Yeah, thank you.
Okay. Okay, Sergio.
Yes, thank you. I was wondering, because this bound that this cutoff scale that we have, isn't it essentially the Planck scale, or is the number of species particularly large. I don't see really how it differs from the Planck scale.
You mean this scale?
Yeah.
Well, we will discuss this next. I mean, this depends on the number of particle species in the extensions of beyond the standard model. Whatever, if you give me your favorite theory of beyond the standard model, motivated by something, then in that theory you can compute a cutoff will be given by this expression. But of course, number of species here so far are not specified. We'll discuss it next once we try to use this for addressing some questions in the extensions of beyond the standard model. So far, this is independent of what is the underlying theory. Okay, if your theory has this number of species, this is what is happening. Okay.
Okay, thank you.
Okay, so another question. Yeah, please.
Hey, quick question. I was wondering if the number of species would depend on the momentum transfer Q or the temperature of the black hole. For example,
no, sure.
if a very heavy particle.
Very good. Yeah, of course. Yeah. In other words, this is what I said. I said that you can have a situation when a number of species can be distributed. In other words, let's draw it like this. Okay, so imagine that this is the energy scale. In other words, this is the scale of momentum transfer. Okay, Q. Let me call it Q. Scale of momentum transfer, and here we have a cutoff, right? So this M star. But the spectrum of species could be distributed here, masses of species. So of course, every time we consider, so for example, if I have a particular species of mass m, right? These species of mass m, they would be active from the point of view of a process with momentum transfer that is comparable to m or above. Okay, so for example, these species will become active in this domain. Okay, activity domain. For example, if I have a black hole of radius much smaller than inverse m, then these particular particle species, they will contribute full-fledged into the operation of a black hole. Okay, they will count as active species. So for black holes with radius larger than inverse mass, so in this domain here, these species will decouple as usual. Heavy particles decouple. They do not. So for example, production of heavy particle in the Hawking operation of a black hole will be Boltzmann suppressed. So for example, production rate from a black hole will be suppressed by the mass of a particle divided by the temperature of a black hole. Okay, at least by this factor. Okay, so therefore, yeah, I mean, number of species, of course, is a scale-dependent notion. But here, of course, this bound puts the bound. Sorry, the bound counts everything below the cutoff. Okay, everything below the cutoff matters. All the particles with masses below the cutoff scale. So correspondingly, the bound is self-consistent. Because that puts the bound, because above cutoff we don't know what is happening anyway. So that's a different theory. Okay. Does this answer your question?
Yeah, that's exactly what I was asking. Thanks.
No. But let's go to exactly what you're asking. So then tell me what is the part that you.
No. I'm saying yeah. You exactly answered my question.
Exactly answered the question. Okay, sorry. Thank you. Okay. Was there anything else? Let me see. There's a. Yeah, so the question is a very good question, excellent question. So is this m star a lower bound on a mass of a black hole? Okay, so in other words, so is the mass m star what says the lowest bound on the mass of a black hole? So the answer to this is a little bit more involved, because the reason is that, strictly speaking, with those arguments that I gave, this gives a bound on the size of a black hole. Okay, on the size of a black hole. Now, what we learn from here, the following thing, that m star is a inverse m star is the lower bound on the size of a black hole. What does it mean? It means that in the weakly interacting quantum Einstein theory in 3+1 dimensions, okay, this by the way, this is generalizable to arbitrary number of dimensions. I'm just simply discussing here 3+1. So within this theory, you cannot have what you would call a black hole, okay, solution that classically would be a good approximation, semi-classically small corrections, quantum, in that theory. So therefore, the inverse, the mass of a black hole must be larger, okay, sorry, the radius of a black hole must be larger or of order of m star. This is what we know. Also, we know that the momentum transfer has to be less than m star in order for the processes, for the scattering amplitudes or any other quantum scattering processes or corrections, quantum corrections, reliably computable within weakly interacting Einstein gravity, the momentum transfer has to be less than m star. This is what we know. Now, it turns out that putting these two together indeed gives you the fact that not only the size, but also mass of a black hole. So this is basically a lightest black hole. At least this is the case in all the known examples. Actually, I will consider one example, so-called extra dimensions, which precisely shows you that. Okay. Okay. Okay, I don't hear any other questions. So let's continue. Oh, no, there is something. All right, okay. Now the question is, so, okay, so you see why these bounds coming from, why black holes are so useful? Because they give us null arguments, the possibility to use, they are tools that give us absolute bounds because these are based on null arguments. You don't have to know what is beyond there. It just simply invalidates. It's sort of a, sometimes it's called, it offers you proof ad absurdum, because you see that based on certain very exactly known properties and knowing that corrections must be small, if you run with the thought experiment into a contradiction, you see that corrections cannot be small, and therefore this gives you an absolute bound on the validity of the theory. And this cannot go wrong because there is no assumption that you have to invalidate one of your assumptions in order not to get a contradiction. Okay, so that's why they are extremely useful. Okay, so now now I will structure the discussion the following way. Now I will mention why this is useful for the standard for controlling certain set of extensions of the standard model, and what are the puzzles that this can help us to answer. Okay, and then I'll go to gravitational dynamics, how really gravity arranges itself towards adjusting to this bounds. Okay, and so this brings us to the puzzle of the standard model that goes under the name of the hierarchy problem. Now the name problem is not okay. Is a little bit controversial. Some authors, they don't like the name of the problem. Instead, hierarchy, it should be called hierarchy puzzle. Okay. So why? Because hierarchy problem belongs to the category of so-called naturalness puzzles. Okay. Or puzzle. And so naturalness puzzles are puzzles that there are still debates how precisely to define what do we mean under naturalness. But they are not, one thing we all agree is that they are not, these are not consistency problems as such. For example, there is no, for instance, anomaly cancellation, gauge anomaly cancellation, and other things, they are consistency requirements. Now the naturalness puzzles are puzzles because we have understanding that something similar is happening somewhere else, and this is resolved by existing of some new physics or something like that, and we see that there is something wrong there, but strictly speaking, they are not inconsistencies of the problem. Okay, so what is the naturalness hierarchy problem? Hierarchy problem, I already touched upon it. I already said that the one way to understand this is why Newtonian gravity mediated by the Higgs, why Higgs gravity, okay, which effective Newtonian constant of the Higgs, which is 1 divided by the vacuum expectation value of the Higgs, okay, which is also a Fermi constant of weak interactions, okay. Why is this much stronger than Newtonian gravity, okay, which is 1 over m Planck square, okay. So this is the issue. Now, this issue is very sharp, okay, and the reason is UV sensitivity of the Higgs mass or the wave, because the wave of the Higgs and the mass of the Higgs are related, to the cutoff. So in other words, the way you can think about it, so there is a naive way, so based on perturbative arguments already, based on perturbative arguments, you can see that Higgs mass parameter. So in the Lagrangian, the mass parameter is the Higgs, right? Higgs mass. So in the Lagrangian, we have mass of a boson. So let's say we're denoting Higgs by h. Let's not confuse that with the graviton. Okay, with the little h, let me denote it by capital H. Okay, for a moment. All right. So we have Higgs particle. I'm talking about Higgs particle, not the Higgs doublet. Although we can talk about Higgs doublet, it doesn't matter. Okay. For this discussion, it doesn't matter. And so this object has self-interaction. Okay. Through the, okay, let's write it like this. Let's discuss doublet. We can discuss doublet right away. Has self-interactions, and of course interactions, Yukawa interactions with fermions. Okay, H psi schematically, right? And also interactions with the gauge bosons, gauge interactions. So now the thing is that the corrections to the square of to the mass term of the Higgs, the corrections to the mass term, and this is true about corrections for a mass term for generic scalar. These corrections, they come from, of course, the infinite series of diagrams. Okay, for instance, I don't know. So for instance, Higgs interacting with a fermion loop, okay, H psi H, or Higgs interacting with itself, okay, H, and so on. And the issue is that these are quadratically sensitive to the cutoff of the theory. Okay, so let me call cutoff m star right away, because anyway we will use this notation. Okay, so they are quadratically sensitive to the cutoff of the theory. And now, one reason for this is that, I mean, the scalar mass is not protected by any symmetry. And so the pseudo-scalar masses can be protected by symmetry, by shift symmetry. For example, for Goldstone bosons, we have this, but the mass of the Higgs doublet of an interacting scalar is not protected by any symmetry, and correspondingly, it is sensitive to the cutoff of the theory. Okay. Now, of course, there are a lot of discussions. Sometimes you can see the arguments which says that this problem is fictitious because this is simply artifact of the way we compute in perturbation theory corrections to the parameters. But at the end of the day, of course, there is one physical mass of the Higgs, and okay, so that's all we care about. And why should we worry about some sensitivity to the cutoff in an intermediate step, and so on? Okay. Now those arguments, so those arguments are pretty much dwarfed, or okay, maybe not completely dwarfed, but at least the hierarchy problem is made real because of gravity. Because remember, we said already that in gravity, the story is different, that in Einstein, in standard model plus Einstein gravity, there is a separation of the between elementary particles and classical objects. And there is no way to have elementary particle in pure Einstein gravity to be heavier than Planck mass. Now, strictly speaking, because in standard model we have particle species, this has to be corrected by the species scale. But at the moment, let me not ignore it. Let me take number of particle species order 1. So I will not make a distinction. Okay, so if number of particle species of order 1 in a theory, then there is an absolute bound on a mass of an elementary particle. And now this makes a problem much the argument pro puzzle much more powerful. Why? Because you have a quantity that is not protected by any symmetry, that in quantum computations is quadratically sensitive towards the cutoff of the theory. So you have quantity here. Okay, so of course the parameters in the Lagrangian are squares. So what I have to compare, I have to compare the square of the Higgs mass to the Planck mass, or square of the scalar to the Planck mass square, because that's the term in the Lagrangian. That's what receives corrections. And so we see that there is a hierarchy which is 34 orders of magnitude or something like that. Okay, and we don't understand why, because there is no fundamental principle that tells us that the mass of this particle has to be so below the cutoff to which it is attracted, because we know that there is sensitivity. Sensitivity is a fact. Whether sensitivity, how the sensitivity translates into the observable quantities, that's a separate story. But there is a sensitivity, and there is an absolute upper bound on the mass of any elementary particle. Now, this of course makes it much sharper, because the question is about this hierarchy. We're not, for example, we're not asking a question why Higgs particle is much lighter than the solar mass. Because naively, if you forget about the fact that Planck mass produces, right? So we are not puzzled by, so here is a Planck mass, and here is mass of the sun, okay, solar mass. And so we are not asking why Higgs is not somewhere here, okay? Because in Einstein gravity gives us a very well-defined answer to that. Higgs cannot have a solar mass because it will not be an elementary particle. No question about that. So now you understand why the question is sharper, because the Einstein gravity eliminates an infinite domain for possibilities of the masses of elementary particles. It leaves a finite domain, and we are finding a particle in the bottom of this finite domain. And so this is the problem. Let's make everything square just to make it. Okay, so let me take questions about this, and then we can make a break. Yes, Omar, please.
Okay, so in essence, what you're saying is that since we already have now we do have, let's say, a scale. If we compute the one loop correction to, or whatever loop, let's say one loop correction to the Higgs, in principle, we should plug in instead of the cutoff, this Planck mass, and let's say Higgs should be of that order of mass, right?
Very good. So very good. Yeah. So that's precisely the correct way of putting it. In other words, the point is the following, right? So suppose you don't know how to control perturbation series, okay? And so you are saying, okay, I have corrections to the Higgs loops. I have corrections to the higher order contributions, this and that. And okay, all possible loop diagrams, okay? Higher order to infinite number of loop order. And so I don't know how to resum them, okay? So at the end of the day, perturbation series must be resummed. There is also a 3-level mass. So at the end of the day, however, indeed, what gravity is telling us is that this, whatever, black box, okay, has a universal cutoff. This cannot generate, no matter what you do, no matter how you compute things, we know Einstein gravity is telling us that no matter what you do, the Higgs cannot have a mass which is larger than the Planck mass. That is impossible. And that's completely independent of UV completion of gravity. Because unfortunately, I didn't have time to discuss that aspect, but because black holes, as you can notice, right? Remember this, we plot this the connection between mass and the Schwarzschild radius, right? Because what black holes do, black holes simultaneously what they do, they convert a would-be UV region of the theory into an infrared region. Okay, so in other words, so we know that this has correction coming from here. This cannot exceed the Planck scale square. Okay, correction to the mass. So in other words, okay, let me reflect on this a little bit. This is because this is extremely important. Now, ordinarily, right? So we are saying that high energies is the same as short distances, right? So this is pretty typical. We use this all the time, this language, but of course we have to be extremely careful. What the short distance is not high energies, but actually what probes short distance is the momentum transfer per elementary particle, a process with momentum transfer. So now, if I switch off gravity in theory without gravity, for example, in QCD, right? QCD is at short distances is a theory of quarks and gluons, and a fantastic theory of quarks and gluons, asymptotically free. Now, in asymptotically free theory, for example, I can probe a distance L, some distance L, all right? So for instance, if you give me a box of size L, I can probe an interior of the box by performing a scattering experiment. And I know that in order to probe interior of the box, I need processes with momentum transfer, okay, with Q larger than 1/L, because I need to scatter wave packets here, okay? And this requires high energies, all right? So therefore, in QCD, if you give me a high center of mass energy, let me call it E, center of mass energy much larger than certain size, I can arrange an experiment or series of experiments. Of course, the coupling can be very weak, so it may take repeating experiments to do the measurement. But I can arrange experiments so that I can probe a substructure of the box, right? But with gravity, the story changes dramatically because so in QCD, high energies, ultra high energies, they probe ultra short distances. But with gravity, the story is very different because, as we discussed, remember that, for example, suppose you give me a box of certain size. You think that you have a box of, let's take a box which is much smaller than the Planck length, right? So naively you have this box. So here is Planck length, and here is the size of the box, okay? So L. And okay, we can naively we can use the same philosophy. We can scatter particles with center of mass energy much larger than the size of the box, 1/L. But the problem with this is that this center of mass energy, once I localize it within its own Schwarzschild radius, will produce a black hole. So a third scale appears all of a sudden. This is a gravitational radius, RG, which we called RG, which is the energy, center of mass energy, times L Planck square. And you can very easily that if energy is much larger than 1 over L and L is much smaller than L Planck, this will be much larger than L Planck. Correspondingly, not only that we are not really probing an interior of a box smaller than the Planck length, we're not even probing a Planck length. So by producing a black hole, effectively high energy gravity, instead of probing short distances, probes effectively large distances, okay? So this is the property of gravity. So this is what gravity does. And that's why this fact that, for example, Higgs or any other elementary particle cannot be lighter, sorry, cannot be heavier than the Planck mass, that's independent of how we complete gravity in UV, let's say above the Planck scale. It's completely independent of that because the endpoints are fixed by physics of black holes, okay? Does this answer at least approximately what you are?
Yes, I would like to have like a small follow-up. Just how are we sure that it is not, as you said, that the sensitivity, the quadratic sensitivity of the Higgs mass to this to the mass scale of Planck is real, let's say? Why are we sure that it is not the way we are computing or renormalizing? I don't know. That's what I want to ask you, let's say.
No, we don't know. That's why I said, I mean, that's why I said that the hierarchy problem is a so-called naturalness puzzle, okay? Now, we don't know. Of course, it may happen. It could be that this is a coincidence, all right? That by some mysterious reason, despite the fact that nature gave us a real cutoff on the mass of an elementary particle, and despite the fact that a quantity that we have is sensitive to that cutoff, despite this fact, it may be that it happens that this quantity is stabilized, happens to be there around the scale, which is much smaller than the Planck mass, without any underlying reason. Of course, we cannot exclude such a possibility. That's why the hierarchy problem is a naturalness problem, because the problem, but also what is very important is to understand that computations are at the level of our understanding of physics of the cutoff. Precise computations are fundamentally impossible, because you understand when you are working within effective field theory and you have a parameter that is sensitive to the cutoff of your effective field theory, it is fundamentally impossible to compute this quantity within your effective field theory by default, because it is a cutoff sensitive quantity, and whatever cutoff physics is there can correct this quantity. And that's why fundamentally it is impossible to compute the mass of the Higgs within standard model plus gravity, because we don't know how to do perturbative computations at the Planck scale. But not perturbative, we don't know how to do computations because perturbation theory at the Planck scale breaks down, okay? What we know for sure that we cannot go above the Planck scale because of the power of black hole physics. That we know. We know that Higgs cannot be heavier than Planck scale. But we cannot really compute whether it's a Planck scale or Planck scale divided by 100 or 1000, okay? Okay, there is another hand. First of all, does this answer your question?
Yes, yes.
This is very important to understand that we are not talking here about computations and the result of computation not matching the observations. We're not talking about that. Yes, Tim, please.
Yeah, just another very short follow-up to make the problem more clear to myself.
Yeah.
So we have this loop corrections to the Higgs mass, and we know they're somewhat proportional to the cutoffs, that is the Planck scale squared, and naively would have expect that the coefficient in front of this correction is order 1. So we would expect the Higgs to have mass of order more or less the Planck scale, but we know there's from gravity the cutoff above the Planck scale. So we could reformulate the hierarchy problem by asking why this coefficient in front of the loop correction is so tiny. So we could maybe assume that there is a cancellation and then a very little perturbation to this cancellation. Is that the right way to think of it?
Yes, of course, sure. You can assume that there is a cancellation. In other words, again, what is very important is that loops are the poor man's way of, since I don't have more powerful language, none of us has, the loops are poor man's way to try to describe something that we don't have full control of. So what I'm trying to say is that cutoff sensitivity, this is not something limited to the perturbation theory and limited to the loops, okay? So there are quantities that are sensitive, quantum corrections to which are sensitive to the cutoff. If you change the cutoff, the quantity changes, and there are quantities which are not sensitive, okay? So for example, fermion masses, remember we discussed fermions, chiral symmetry in fermions. So in fermions, if I have fermion with a, let's say, conserved charge, okay, so the mass of Dirac fermion is left, right, and there is a chiral symmetry, or I can also write it in Dirac basis, okay, psi bar psi. And there is a chiral symmetry under which fermion transforms, which is explicitly broken by the mass term. Correspondingly, the mass term of the fermion is not UV sensitive, is not too much UV sensitive, it's only logarithmically sensitive. In other words, the fermion mass gets renormalized through itself. So correction to the mass of the fermion, quantum correction, must be proportional to the mass of the fermion. Because if at the 3 level, the fermion mass goes to 0, and then chiral symmetry makes it sure, okay, that fermions do not generate a mass. Let me put aside the story with anomalies, okay? So you don't generate a mass. So this is the reason. There is nothing like this for the scalar, and scalar by default is ultraviolet. The mass of the mass square of the scalar is ultraviolet sensitive quantity. Okay, so that is there. Now, how much the sensitivity manifests itself that depends on a theory and computations in a theory. Now, there are theories in which we can compute this. For example, as you mentioned, cancellation. For example, there are supersymmetric theories in which, for instance, what may happen is that here is Higgs mass, and here is a new scale where cancellations set in, okay? So bosons and fermions, they compensate each other. Unfortunately, okay, since the time is limited, the supersymmetry, okay, of course, there's, some of you probably have taken, I'm sure have taken courses on supersymmetry and you know what it is. But in any case, this is a cancellation mechanism, okay? So for example, supersymmetry introduces additional degrees of freedom, and they can cancel these loop diagrams. And in that case, you can see that the theory regulates itself loop by loop or even non-perturbatively. So yeah, sure, that can happen, and that's one example. The question is whether this can happen without any new physics from MH to M Planck. All right, so that's the point. Now, such things earlier, for example, in QCD, we have observed situations when there exist scalars, but there is new physics nearby that tells us why scalar masses are where they are. And so the question is, what is the similar mechanism for the standard model Higgs mass? Okay. Okay. I hope so. Let's make a short break since there are many questions. Let's make a short break. Let's see. How much time do we have? What till the end of the lecture? We are finishing. So now is what? What time is it?
Yeah, we are finishing at 4:30.
Yeah, and now
yeah, we are 3/4, so maybe 6 minutes would be a good break.
Okay, so 6 minutes. All right, let's make 6 minute break. Okay. All right.
Yeah.
Okay, very good. So let's continue with this, and then we also have a discussion session, so we can discuss more questions during that session. So now the question is, so therefore, one possibility of addressing this issue, let's discuss that possibility to do what we just discussed, that in reality, as we have seen, what species show us, the species discussion, what it shows us is something very important, because what it tells us is that the cutoff, real cutoff of theory of gravity is not Planck scale. Planck scale sets the coupling of Einstein graviton, but that's not the scale where gravity becomes strong. So there is a hierarchy between the two scales, in particular given by the number of species. So in other words, species open up a possibility that the cutoff is not Planck mass, but can be something arbitrarily smaller if you take large number of species. So of course, this may also trigger our thinking in this direction that species may not be the only possibility for doing that. So it's, in other words, it liberates the cutoff from the Planck scale, okay? So therefore, one possibility would be that actually the gravitational cutoff itself is lowered down to some low energy, okay? So M star. Of course, the gravitational cutoff can only be lowered down to the scale, which doesn't contradict to experimental observations. And currently, we have probed pretty well the standard model up until LHC energies around TV, few TV. So this is something few TV, okay, to which we can potentially lower the cutoff. Now let's step a little bit back from this. So far, you see how I'm structuring the discussion. I'm saying, okay, look, Planck scale cannot be elementary particle heavier. It's an absolute non-perturbative cutoff. And however, that's an absolute upper bound on the cutoff, but real cutoff can be much lower. And here is an example how a theory can disentangle the real cutoff from the Planck scale through existence of many particle species. Okay, so now let's put aside for a moment the species necessarily, and therefore look at the big picture. So the big picture is the following, right? So we were saying, so here is gravitational alpha gravity, okay, as a function of scale q, momentum transfer, right? And so here's the alpha gravity, and so here we have Planck scale somewhere, okay? And so here we have, let's say 1. And what is happening is that in Einstein gravity, so in Einstein gravity, essentially gravity is extremely weak, and then very quickly around Planck scale becomes strong. So it reaches 1, this bound on strength, of quantum strength, around Planck scale. And so what this discussion about species tells us that the scale could be somewhere else, okay? Not necessarily generated by species. Species is an example. They show us how the two scales can be separated. So things may happen earlier, okay? So gravity may go out of perturbative regime earlier. And so the question is, how can we understand this? All right? So how can we understand gravity becoming stronger in general? What makes gravity stronger or weaker than Einstein gravity? Let's ask this question, okay? Now, the great thing about quantum field theory and weak coupling domain of quantum field theory is that many important questions, we can approach from the domain of weak coupling, okay? And of course, once we hit the strong coupling, the theory goes out of control, obviously. But the tendencies we can capture very powerfully, even within weak coupling approximation, so within a theory. On top of that, there are certain statements in quantum field theory, certain tools that go beyond, that are non-perturbative. They go beyond perturbation theory, and they even go beyond weak or strong coupling, certain quantities, certain criteria, okay? Now, so here, let's ask the following question. So in quantum field theory, suppose I have energy momentum tensor, okay? And I want to understand, so gravity mediates force between two energy momentum tensors, okay? So there is an exchange And there is a mediation of force between two energy momentum tensors. Okay, so now there is a so in Einstein gravity, this is mediated by a graviton. So we discussed this, right? By canonical normalized graviton. But suppose we want to ask the question in more general terms, okay? So the question is, I know that I have energy momentum tensor, another energy momentum tensor, and something mediates force between them. So, okay, what is the structure of that something? Okay. In other words, there is exchange, there is a messenger between two energy momentum tensors, okay, which creates what I would call gravity. But what is the generic structure of that messenger? Okay. So in other words, that generic thing, object that mediates this exchange, reduces to a correlator. Okay. So for example, in an S matrix, if I'm considering an S matrix element, let's say d for x prime, t mu at x, and let me call this mysterious object, whatever it is. Let me call it h mu nu. All right. Point x, h alpha beta at point x prime, t alpha beta at point x prime, and a contraction. All right. So effectively, this object, this contraction, is a Green's function. So there is a messenger that mediates force between two energy momentum tensors, and this messenger has a Green's function. Okay, so there is a Green's function of this messenger, g mu nu alpha beta. Okay, this contraction. Okay, so now in quantum field theory, there exists an extremely powerful tool of understanding the structures of Green's functions through spectral representation. Okay, so for example, you have probably seen it in QFTs. In quantum field theory, for example, if I have a propagator, let's say a momentum representation, a Feynman propagator, a momentum representation of some object, okay, right, scalar, I'm saying in the scalar case, it has spectral representation, which we can write as, let me write it as dm square rho of m square p square minus m square, and for Feynman it will be I epsilon. Okay, I mean I epsilon is simply stands for what kind of prescription you want to use for the whether you want to have retarded, causal, and so let me focus on causal on Feynman propagators. Okay. So there is the general structure of, for example, for the scalars, I'm sure you have seen it. There is a similar for tensors. Okay, so there's a similar structure for tensors. So in other words, what does this mean? This tells us that if I have a scalar force mediated between two sources. So let's say I have a source in the theory. Let's call it j of x in order to distinguish from the energy momentum tensor, and let's say this source couples to some operator, scalar operator x, and this mediates an exchange. Okay, so we are exchanging x, so we have source j of x, and there is an exchange by this f of x between two sources. Okay. Okay, of course, here should be a Green's function. Gx minus x prime. Okay, so basically what this spectral representation is telling us is that we can understand this exchange as sum over many different exchanges, many different scalar propagators, okay, each entering with the weight rho of m square. Okay, so an arbitrary scalar exchange between two sources you can understand as a tower of exchanges with different masses which enter with different weights. Okay, there is nothing else, and this is very important. So in other words, this follows from the causal structure of QFT, of quantum field theory, that quantum field theory with right causal structure, which imposes certain analyticity properties on the Green's functions, it tells you that an arbitrary exchange you can understand in terms of tower of exchanges of, let's call them elementary exchanges. Okay, for each contribution, let's say there is some elementary exchange. Okay, so the same is true for spin 2, obviously, for tensor. Okay, so for tensor, what will happen is that, let's go to momentum representation again, for instance, and will be a similar representation of these exchanges. dm square with certain p square minus m square I epsilon with certain spectral function. Sorry. With certain spectral function. But of course, this spectral function now will have some tensorial structure accompanying it. All right. Now, if we understand what is this, what are the limitations of this on this? We essentially understand this picture. We understand how to achieve anything like that, approaching things from the domain of validity of QFT. Okay. Okay. No, I thought there was a question. Sorry. Yeah. Okay. So now, how to understand? So basically, what this tells us is the following thing: the tensorial structure uniquely tells us if there is something that mediates gravity between two energy momentum tensors, and that's what gravity is. Okay, force between two energy momentum tensors, that is reducible to a tower of exchanges of tensorials with different masses. So what are these tensorials? These tensorials are spin 2, massless. This we already know. This is Einstein graviton. Spin 2, massive, and a scalar, massless or massive. There is nothing else there. There is nothing else that can mediate force between two conserved energy momentum tensors. Okay. So therefore, to complete this knowledge about the tensorial structure, so tensorial structure of m equals 0, mu nu, alpha beta, we have already derived. That's sorry, that's a tensorial structure of Einstein graviton. And we can write it as, of course, it's gauge dependent, but in particular gauge that we wrote it as okay, this is the tensorial structure for m equals 0. Now the question is, what is the tensorial structure? Of course, this multiplies Newton's constant, obviously. So this multiplies ordinary Newton's constant, or 1 over m Planck square. So now we want, let's call it G simply. Yeah, let's call it G. And so now we want to understand what is for non-zero. Okay. In order to understand this, there is a question, right? So the question is whether the Green's function of graviton is related to the supermetric of Wheeler-David equation. No, I mean the Green's function of the graviton is what we already discussed. This is Green's function in that you can derive at the level of Einstein gravity. It's simply linearize Einstein gravity. You don't need to go beyond that for this tensorial structure. Okay, so this is Einstein gravity constructed as S-matrix theory on Minkowski background. So this structure, we're focusing on that Minkowski background S-matrix theory order by order, introducing nonlinearities and couplings. Okay. I mean, presumably there is some relation with Wheeler-DeWitt, but I mean, we don't have to go there. Okay. Does this answer your question? I mean, gravity is gravity, of course. Gravity is obviously, wherever you have gravity, the things are related. But this is simply an Einstein gravity constructed as an S-matrix theory. Okay. I don't know whether this answers your question, but we can. Okay, great. So now for this, we need to understand the Green's function. What do we need? We need Green's function of spin. So spin equals to mass non-zero. Okay. So the generalization of linearized Einstein to linearized theory with non-zero mass. So generalization is very similar to generalizing the Maxwell to Procca. Remember, we generalized Maxwell to Procca. Okay, it's very similar. So let's do that generalization. Okay, so in Einstein, let's do it at the level of, okay, doesn't matter, level of Lagrangian. At the end of the day, we'll write the equation. So in Lagrangian, we had linearized Einstein Lagrangian, right? And we had, so in linearized Einstein Lagrangian, we had the linearized Einstein tensor. So Lagrangian is this, up to a coefficient, of course, which is not important for this discussion. And this had a gauge redundancy, right? Okay, so there was a gauge redundancy in this Lagrangian. So now we can add a mass term, but there is a choice for adding a mass term. There is a choice of different contractions. So for example, we can contract h mu nu with h mu nu, or we can take the trace and square the trace. Okay. So it turns out that there is a unique relative coefficient between the two, which comes from the requirement that we don't want to have unwanted degrees of pathological degrees of freedom. Okay. So this will become clear in the course of discussion in a moment, but actually this term, of course, doesn't maintain this gauge redundancy seemingly. So similar story with Procca, right? Just like in the case of Procca, this redundancy is gone. However, we have to be very careful, because by adding a mass term, we are changing theory discontinuously. So correspondingly, h mu nu is no longer the same object as Einstein graviton, and correspondingly, we are changing the degree of freedom. And so we have to remember that h mu nu is a different object from Einstein graviton now that we have added the mass. Now I could have added a symbol m here, but in order not to carry this m around, just remember that h mu nu, not Einstein graviton. Now this theory has a name. It's called Peirce-Pauli theory of linear gravity. So it's like a very Procca. It's like Procca versus Maxwell, Peirce-Pauli versus Einstein. So let's study this theory in order to derive the tensorial structure. And so for this, we can write the equation directly, right? And equation now has the form, again, linearized Einstein tensor. Please remember, I'm not changing notations, but please remember that h mu nu is not Einstein graviton in this particular case. Box H minus d alpha h alpha nu. Again, I told you, this may look a little bit complicated, but actually it's not. The structure is very clean and unique, and fixed by gauge redundancy. And so now we are adding a mass term. Okay. And so the corresponding equation is h mu nu minus eta mu nu h. And this is equal to energy momentum tensor. So for a moment, let me rescale the coupling constant there, and then I'll take it out. So coupling constant is rescaled into the energy momentum tensor. Okay, so we're going to study this equation, this expression. Of course, now, so the question is, how many degrees of freedom are there? How many degrees of freedom does this theory propagate? Okay, and so of course we can no longer use gauge redundancy to fix to reduce number of degrees of freedom. However, we have a constraint. Okay, because if we take derivative of this expression, if we take divergence of the equation, okay, if we take divergence of the equation, so there is a term here equals to T mu nu. If we take divergence of both sides, the Einstein tensor, divergence of Einstein tensor is 0. Okay, and so we are left with the constraint, which is similar to what we had for Proca for a vector field. Okay, so we have essentially divergence of this object. So this is d mu h mu nu minus, or basically divergence of this is equal to d nu h. Okay. Now this looks like the gauge that we fixed in gauge redundant theory, but of course here this is not a gauge fixing. This is a constraint. Okay, this is not a fixed. This is not a fixed gauge. So now what we can do, we can use this constraint, plug it back there, and see what happens. And so to simplify, instead of using gauge, and you can see what happens. So first two terms, we'll keep it as they are. Then from here there will be a term which will give me d mu of d nu h, right? This object. Then the similar thing there, minus d mu h from this second term. Then there will be, these terms will be copied simply, right? This term will be copied, d nu h, and then there is eta mu nu, and so derivative is derivative with respect to alpha, so it'll be box h, if I didn't make any mistake, I hope. Okay, we get this, right? So then what happens? This cancels, and we are left with the form h mu nu, which contains h mu nu, and which contains the trace. So now this constraint eliminates 4 degrees of freedom. So after this constraint, we are left with 10 minus 4, and so this is 6, okay, degrees of freedom. But now we can notice that, let's take trace, okay? So if we take the trace, we get that box h minus so sorry, this also cancels. I'm sorry. And so we have box h and minus box h. Ah, sorry, I forgot the mass term. I'm sorry. There is a mass term, of course, m square h mu nu minus eta mu nu h, and this is t mu nu. Okay. So now what happens is that if I take a trace, this term, box h, this term gives me box h, and this also will give me box h, and they cancel this term. And so we are left with this, and this gives me h minus 4h, so minus 3. Oh my God, this minus 3 h, and this is trace of t. So basically what we get is that trace is minus 3m square trace of energy momentum tensor. So in other words, trace is something non-propagating in the sense that it's defined through the trace of the energy momentum tensor through the algebraic equation, okay? So this gives us yet another constraint. And so we are left with yet another constraint on the number of degrees of freedom. And so we are left with 6 minus 1, 5. So we are left with 5 physical degrees of freedom propagated by Pauli-Fürst Pauli first graviton. Now, we can go back and use in the equation, right? We had this equation. Sorry. Right? So we can use this condition. We can plug it here and here, right? And then put these things on the other side. So what do we get? We get box plus m square h mu nu. And here we get t mu nu, right? And we get the following structure, right? So minus 1/3 of eta mu nu minus d mu d nu plus d mu d nu m square t. Okay. Watch out. I may make some sign mistake, but okay, nothing important. Nothing important that affects the story, but still better not to make any sign mistakes, coefficients. So here, so we got this type of structure. Okay. Now, therefore, h mu nu produced by a source, of course, now we can invert this. H mu nu produced by a source, T mu nu, now has the following structure, where this is T mu nu minus 1/3 eta mu nu m square T. Okay, so this is the action. Okay, so now the exchange, so this fixes the exchange because now effectively this convoluted with a probe source, right? This will be T mu nu 1 box plus m square T mu nu, but since source is conserved, we can forget about derivative part and we get minus 1/3 eta mu nu T. Okay. So therefore, this fixes, of course, this fixes the correlator, the structure of the correlator. So in other words, T mu nu, this is nothing but T mu nu G mu nu of massive Pauli first graviton, okay? This is alpha beta, T alpha beta. This effectively is this quantity. So it's equal to this, okay? So this is the exchange, fixed by exchange. So in other words, the among two conserved sources, oh, there was a discussion in the chat whether it's correct with plus 1/3 or minus. I think minus 1/3 is correct, but anyway, so we can come back to this. This is not important. So you mean here? No, here is correct. Minus 1/3. Yeah. So now, therefore, now notice notice there are two differences from the massless case. Okay, two differences. So first, if I take the limit when m goes to 0, the massive exchange doesn't reproduce massless exchange because there is a difference between 1/3 and 1/2. Because for massless, strictly mass equals 0, the exchange was T mu nu 1 over box T mu nu minus 1/2 eta mu nu T, okay? And here we have T mu nu 1 over box when mass goes to 0, but the 1/3 cannot jump to 1/2. So it still is minus 1/3, okay? So in other words, this is a manifestation of the fact that there is an extra degree, extra polarization contributing into the exchange. In other words, you see that the attraction is stronger because repulsion is weaker. In other words, -1/3, and here we have -1/1. So massive gravity, massive spin 2 is more attractive with all the other parameters fixed than massless spin 2 between the two sources, because there is an additional scalar polarization which contributes into this attraction. Okay, so now this tensorial structure is unique, and it follows from the fact that Pauli-Fierz Lagrangian is unique. The structure is unique both in the mass term and in the kinetic term. Kinetic term is just simply linearized graviton. And correspondingly, now we can write down in full glory the most general Kjellin-Lehmann expansion. This is, by the way, Kjellin-Lehmann expansion of the spectral representation, right? Okay, so this representation. So we can write most general one for gravity. Okay, so for gravity, most general. Okay, we can write it in momentum representation. So alpha beta most general for gravity will have the following structure. So the first, there will be an exchange with massless graviton. Let me normalize that to 1/m Planck. 1/m Planck square. Let me call it just simply 1/m Planck, whatever is the exchange of massless graviton. That is, or Newton's constant, which is the same. Okay, G Newton. This is simply G Newton. Okay. So this has this structure, or yeah, okay, we can write it as in form of eta mu. That doesn't matter. In terms of exchanges, we could also write, but let's write it in terms of eta mu. So it would be eta mu alpha, eta nu beta plus symmetrized minus 1/2 eta mu nu eta alpha beta, and here we have p squared plus I epsilon. Then we have tower of massive ones, m square non-zero, of course m square positive. And here, of course, we can again normalize it to, we can put an overall strength to be 1/m Planck, but then each will come with a coefficient. So that will be a coefficient, let me call it C of m. These are unknown coefficients, okay? And there is a structure, p square minus m square plus I epsilon. Here we have minus 1/3. Now here, I'm assuming that the exchange is through between two conserved energy momentum tensors. So therefore, I'm ignoring this part in the story, this part. This part is otherwise very important because there is a longitudinal polarization which has a coupling which is singular in the mass. But for this discussion, that's not important. Okay. We have this with corresponding spectral. So basically, the spectral function I have traded for C of m. Okay, so C of m is effectively a spectral function, right? C of m divided by m Planck. And finally, there will be a trivial scalar exchange. Okay, so which we can again normalize to m Planck scalar. So this is let's give some coefficients. So this is spin 2, okay, massive, and this will be spin 0, massive or massless, doesn't matter, because here mass is larger or equal, and here we simply have mu nu alpha beta p square minus m square plus I epsilon. So that's it. There is nothing else we can have. A vector is not possible because what we discussed, because vector cannot couple to the conserved current. It will make it because of conservation of the current. So this is the maximum. So now you see, this is why it is important, this expression, because this illustrates how powerful is effective field theory, quantum field theory, because analyticity structure and causality of the theory uniquely fixes what can be the structure of gravitational exchange between two conserved energy momentum sources. Okay, and this is a more general spectral representation for the propagator that of whoever mediates a force between two conserved energy momentum sources. Now, for example, let's finally, I have 3 minutes. So to illustrate what is very important is that all these coefficients must have the same sign. Okay, I mean, overall sign here I normalized to plus. That means that Einstein gravity is attractive, of course, right? And all the others must be also attractive. In other words, there is no elementary exchange with well-defined representation of the Poincare group that could give you a repulsion between two conserved energy momentum sources of matter. Okay, this is extremely important. So what this Chern-Lemon expansion is telling us, that you cannot have anti-gravity as long as your quantum field theory makes sense, of gravity makes sense. No anti-gravity, even at the level of elementary exchanges. Each elementary exchange, because each exchange is a well-defined representation of the Poincare group, has to be attractive. For example, for instance, let's consider non-relativistic energy momentum tensor. Okay, so non-relativistic energy momentum, but this is a massive particle, right? So we discussed this in the previous in one of the previous lectures. So we can take only T00, some mass, and localize the delta function. Okay. Now then, the potential mediated, for example, between this and the probe, tau mu nu, which can be a probe, localizes some distance. Let's say this is x, and the other one localizes some distance. Okay, the potential V of R mediated because of this exchange, so tau mu nu, T mu nu, and sum of all these exchanges. So this will have the following form. So it will have ordinary Newtonian gravity. So let's write it like this. So it will be ordinary Newtonian gravity. We can take 1/r out. Okay, let's write separately. So better. So Newtonian gravity, ordinary Newtonian gravity, okay, plus tower of Yukawas. No, let me denote this by something else. Let me call this mu. Tower of exchanges, okay, that come from C of M with coefficients. Okay, so let me rescale them. Let me call them G Newton's constants of these massive objects of this sort. Okay, so this comes from massive spin 2 and massive spin 0, and also we can have additional force coming from massless spin 0. So let's normalize all of them negative, and we can also have G of 2 of 0, spin 0. So these are coming from spin 2s plus spin 0s. Okay, let's write them separately. I'm sorry. So will be massless spin 0. And then there will be spin 0 massive. Okay, so that's it. So all of them give attraction. So now you see what's happening. If you go towards shorter and shorter distances, and I think I have to finish. So what happens is that at short distances, more and more active gravitational elementary exchanges appear. And so they make gravity stronger and stronger, okay? So for distance r less than, so for any distance r between two sources r, the particles with mass less or of order inverse r contribute effectively, okay? So in this exchange. So correspondingly, since all the exchanges are positive and particle masses are in some spectrum, gravity can only become stronger in ultraviolet before hitting the cutoff. Then this is a very important statement, directly follows from the Chelan-Levin expansion of the graviton propagator. Okay, let me finish here. And yeah, I guess we have a discussion session after.
Thank you, Gia.
Okay.
So we'll talk again
in 1 hour, right?
We'll meet again in 1 hour.
Okay.
Bye-bye.
Bye.